In Chapter 8, we looked at testing claims for one proportion and then for one mean. And then in Section 9.2, we looked at testing a claim about two proportions. And so now in Section 9.3, we're going to look at testing claims about two means. Now, specifically, these are from independent samples, and we'll deal with dependent samples in a bit. And I'll explain what I mean by independent versus dependent here in a second. So again, just like before, we're going to look at the p-value method and the critical value method. But a lot of this should look very familiar. The main difference will be the test statistic that we use. Also, since we're dealing with means, instead of dealing with the normal distribution, we're going to be looking at the student t-distribution, just as we did for testing claims about one mean. So let me look at the definition of independent versus dependent. So two samples are independent if sample values from one population are not related to or paired with the sample values from the other population. So for example, if we were measuring the blood pressure of 40 randomly selected men and 40 randomly selected women, and we wanted to compare the two blood pressures, those would be independent because the men are not paired with the women necessarily. However, if we were measuring the blood pressure from 40 randomly selected married couples and comparing the group of men to the group of women, then they're dependent because the 40 men could be paired up with their wives, in which case we've got dependent samples. So in this section, 9.3, we're specifically looking at independent samples, and we'll deal with the case of dependent samples in section 9.4. So the tools for testing a claim involving two means, the main thing we're interested in is that test statistic. So when there are two means involved, this is our test statistic. And you may remember when we looked at two proportions, the population proportion from each sample disappeared because of our null hypothesis saying that these are equal. Well, now that we're talking about the mean, we're going to have the same thing happen. So our null hypothesis is going to assume that the population mean from the first sample is the same as the population mean from the second sample. So that'll simplify our test statistic calculation a little bit into just the same thing without the minus the mean 1 minus the mean 2 at the end. So we've got our sample mean from our first sample and our sample mean from our second sample. What we've got under the square root in the denominator, this is the sample standard deviation squared, which of course is the variance, for the first sample, and the sample standard deviation squared for the second sample. And then of course N1 and N2 are the sample sizes of each of those two samples. So let's look at the p-value method, and I'll just do an example of the p-value method and one from the critical value method, because at this point you should have the general idea of both of these methods down. We're just going to do this for the case where we're talking about two sample means. So take a look at this example. The mean tar content of a simple random sample of 25 unfiltered cigarettes is 21.1 milligrams with a standard deviation of 3.2 milligrams. The mean tar content of a simple random sample of 25 filtered cigarettes is 13.2 milligrams with a standard deviation of 3.7 milligrams. Test the claim that unfiltered cigarettes have a mean tar content greater than that of filtered cigarettes. So one of the first things we need to do is label our two samples. So in other words, I want to label sample 1, or my population 1, to be the mean tar content of unfiltered cigarettes, which means mean 2 will be the mean tar content of filtered cigarettes. So just to keep those straight, now we're going to identify the claim here and write it in mathematical symbols. And what we said was that the mean tar content of unfiltered cigarettes is greater than the mean tar content of filtered cigarettes. In other words, what we're testing is to see if the filters actually do have an effect. So step 2, same as before, we're going to identify the opposite, and in this case it'll be that mean 1 is less than or equal to mean 2. Now we can, from these, get our null hypothesis. And of course, the null hypothesis will come from the one of these that has the equal sign in it, which means the alternative hypothesis will come from the other one. So in this particular case, our null hypothesis is going to come from the opposite, and our alternative hypothesis will come from the claim. So that means we're dealing with a right-tailed test. Our significance level, since it's not given, we're going to use 0.05. So now step 5, we'll calculate the test statistic using the formula we just saw. Plugging everything in and throwing it into our calculator gets me a t-score of 8.075. So now we'll determine the p-value using the t-distribution table, but of course that's going to require us to calculate the degrees of freedom. Now if you recall, the degrees of freedom in when we previously talked about one mean came from the sample size minus 1. However, now we are considering two samples, so what we're going to do is take the conservative estimate and use the smaller of the first sample size minus 1 versus the second sample size minus 1. So we'll take whichever one of those is smaller. Of course, in this case, since both sample sizes are 25, we'll just take the degrees of freedom to be 25 minus 1, or 24. But in general, take the smaller value. So now let's look at the t-distribution in the 20 degrees of freedom row 24, and we'll get the p-value, or an estimate of the p-value anyway. So I'm looking at my degrees of freedom row 24, and I look for my test statistic 8.0, of course, rather 8.05, but of course that is not in this row. But looking at the trend of my t-scores, I should be somewhere over here to the right of 2.797, which means my p-value, if I follow the trend up here, my p-value should be less than 0.005. So I know that my p-value is less than 0.005. The next step will be to compare this to the significance level. So let's compare our p-value to our significance level, and we see that 0.005, our p-value, is less than the significance level, so we can reject the null hypothesis. Now the final step, of course, in step 8, we need to interpret those results in terms of our original claim. So our original claim was that the mean of unfiltered cigarettes, the mean tar content of filtered cigarettes is less than the mean tar content of unfiltered cigarettes. So, since we rejected the null hypothesis, it does appear that there's enough evidence to support the claim that unfiltered cigarettes have a mean tar content greater than filtered cigarettes. So now let's look at an example where we test the claim of two means using the critical value method. The heights of a simple random sample of 9 supermodels gives a mean of 70 inches and a standard deviation of 1.5 inches. A simple random sample of 40 women who are not supermodels gives a mean height of 63.2 inches and a standard deviation of 2.7 inches. Use a 0.01 significance level to test the claim that the mean height of supermodels is no different than the mean height of women who are not supermodels. So first of all, we'll identify the claim, and to do that, let's first identify which one we'll call mean 1 and mean 2. So I'm going to call mean 1 the mean height of supermodels, which means mean 2 will be the mean height of women who are not supermodels. So the claim is that there's no difference between the mean height of supermodels and the mean height of non-supermodels. That is, mean 1 equals mean 2. So the opposite then is going to be mean 1 does not equal mean 2. And then from there we can get our null hypothesis. Of course, the one with the equal sign in it will be our null hypothesis, and the other one will be our alternative hypothesis. And this, of course, tells us that we're dealing with a two-tail test. So the significance level we're given in this problem is 0.01. So step 5, we'll calculate the test statistic, just throwing everything into the formula. that we have for a test statistic for two means. And calculating this, I get a test statistic of 10.343. Now let's determine the critical value because we're dealing with the critical value method. So we'll use the t-distribution table, and first of all, let's get the degrees of freedom. Of course, it's the smaller of n minus 1 and n minus 2, n2 minus 1. So the sample size of the supermodels was 9, which means n1 minus 1 will be 9 minus 1, gives us 8. And the sample size for the women who are not supermodels was 40, so we get 40 minus 1 is 39. So the smaller of those two, of course, is 8, so we're going to use the degrees of freedom to be 8. So on our t-distribution table here, our degrees of freedom is 8, so we'll be in the 8th row here. Now, since this is a two-tailed test, we have 0.01 significance level in two tails. So we're going to be in the leftmost column, which means our critical value is 3.355. So we found our critical value to be 3.355, but of course, since this is a two-tailed test, we also have to consider the negative 3.355 critical value. However, since our test statistic is positive, we're only going to compare it to the positive version of our critical value. Of course, if our test statistic was negative, then we want to see, is it further away than the negative critical value? Since this was a two-tailed test and our test statistic was positive, and because it was greater than the positive critical value, we reject the null hypothesis. So, since the claim was that the two means were equal, and the null hypothesis came from that claim, since we rejected the null hypothesis, we can say there's enough evidence to reject the claim that the mean height of supermodels is no different than the mean height of women who are not supermodels.